Okay, so chapter 8, objective 7. So we're going to be working with what's called Taylor polynomials, and we're going to also look at how a Taylor polynomial can approximate transcendental functions. So how can it approximate, our first example will be how can we figure out what is the square root of 1/2 in an approximation, but it can also be used to figure out, what is the natural log of 2? What is the sine of, pi over 15? So a Taylor polynomial can approximate any of those types of values. At least that's what 8.7 will be about. And then we'll expand it. Instead of being a finite approximation, we'll look at it in an infinite sense so that we can actually figure out the value of it instead of an approximation. But our approximations can be pretty spot on. So the first thing we have to look at is how do we define it? So how do we define what we call a Taylor polynomial and a Maclaurin polynomial? And it will be nth, meaning we'll look at it in a finite sense, where n will represent our derivatives. Okay, so n will be our derivatives, so keep that in mind. And then our c value is what we're going to be centered about, or anchored or expanded. So there's lots of different ways to say that. So when we're talking about something is expanded or centered at C, keep in mind that sometimes it will say something along the lines, you will be about the value x is equal to. So don't always anticipate that you're going to be saying C is 12. So sometimes they'll say you're centered about x equals, or you're about the value 12, or whatever it is that you're looking for. So keep that in mind. So this right here is our polynomial, our Taylor polynomial expansion. And this is something that we need to make sure that we really either memorize or try to come up with a way to do that. But this is the generic term, which generates each one of these terms before it. So even though this says f of c, keep in mind that I could write this as x minus c to the power of 0 over 0 factorial. So if n were 0, so meaning we're not taking a derivative. So if we're not taking a derivative, that's why there's no prime here. And then x minus c to the 0, all of that is just equal to 1. And then 0 factorial by definition is also 1. And that's how you get that f of c. So then if we're looking at f prime of c, so again, we don't have everything attached to it that follows this pattern, but it is there. So if we have f prime of c, so f prime meaning that's the first derivative, and so then the power would also be 1, and then we would be dividing by 1 factorial. And so that's where all of these pieces are falling into place, right? That's factorial. So this is the second derivative, so a power of 2 divided by 2 factorial. So if we were doing the third derivative, this would be a power of 3 over 3 factorial. And so that is what our polynomial expansions are going to look like. Okay, so super important that we know this expansion because we will be using it and referring to it often. So the other polynomial that we have is what we call a Maclaurin polynomial, and the Maclaurin polynomial is just when we are centered at 0. So if we have a center at 0, then that is a specific type of Taylor polynomial, and it would be a Maclaurin polynomial. And so then the only thing different is the c then would just be 0, and so we would have an evaluation at 0. So that is in general what we are looking at. So what is this whole business about being centered, anchored? What does that even mean? Okay, so let's talk about that. So I'm going to just write in the space below here just to kind of refer to this question a little bit, give us an idea of what we're talking about. And then as we go through that problem, we'll discuss it even further. So what we have here is we have this function of the square root of x. Okay, so don't write this down. We're just looking at, in general, what is this referring to? Well, that certainly isn't what that looks like, is it? Let's try that again. Square root of x. Okay, so this is our function square root of x. So here they want us to use 4 derivatives, right? N equals 4, so we're going to go out to the 4th derivative, and we want to be centered at 1 or anchored at 1. So we'll say 1 is right here. So we have this ordered pair, which is 1, comma, square root of 1, which is 1, right? And we're going to use this polynomial that we create to approximate the square root of 1/2, okay? So keep in mind, so we have this function f of x, which is root x, and we want to know what is the square root of 1/2. Well, unless we have it memorized or we have a calculator handy, this would be like, yeah, good question, Mrs. Pape. So what we're going to do is create a polynomial. So what is a polynomial? So we'll just use P. Sometimes I'll use T for Taylor, and we're going to go out to the 4th derivative. Okay, so I'm going to totally make this up because this is not the right one. But let's say that we have a polynomial of x cubed. It's not this, but we're just pretending minus x squared plus 1, right? So that's a polynomial. So a polynomial meaning we have integer or non-negative integer powers, right? So x to the -3 would not be a polynomial, right? It needs to be a non-negative integer, exponent. And so that is a polynomial. Okay, so if I asked you to evaluate this at 1/2, right? If I'm like, hey, substitute in 1/2, you might dread it doing all the fraction work, but it is not beyond your ability, right? Like this is certainly a number that you can come up with, right? So whatever that would be, right? 1/8 minus 1/4 plus 1. And then what would that be? Negative, let's see, 1 minus 2 is -1. Plus 8 is 7. I don't know, 7/8. That totally could be wrong. And even if I don't know that decimal, I can certainly do long division to figure out what that decimal is, right? How many times does 8 go into 70? It goes in, 8 times, 64, subtract, yada, yada. So this I could evaluate because it's a polynomial and because I know long division. This right here, don't know. Need a calculator for that. So what we are doing, right, is we're creating a polynomial that we can evaluate by hand to determine, what does the square root of 1/2 actually equal to, right? Like, so that is like kind of what we're doing here. So that gives you kind of an overview of that. And so the whole anchored about, so let's go back to that component. So what we need to do to have a function that is going to approximate the square root of x is we have to start with a common point. And so that is what we call our anchor point. So we're going to say there's a common point, and then we want to find a polynomial that will approximate that. So would a line be a really good approximation for that? And I'm hoping your answer is no, Mrs. Pape, that would be horrible. So we wouldn't use a line, but could we use maybe a negative quadratic? Like maybe we could find a quadratic that was not too shabby. So that's what we're looking for, is we're trying to, we start at a common point and we start developing a polynomial around that common point, that anchor point, that center, that will give us an approximation. And the reason that we choose the different center pieces, like you will never make that choice, like it will always be given to you, is because it has to be a known value, something that you don't need a calculator for. So like I would not want to center this at 2 because I don't know the square root of 2. But I could center it at, say, 1/4 because I do know the square root of 1/4, right? So you work with pieces that you know values for based upon that definition. Okay. So that is kind of an overview. So hopefully that made a little bit of sense to you. If not, that's okay. It will. Eventually it will. All right, so let's go ahead and do this particular problem. So we're going to just write our steps off to the side here. So they're asking us to find the nth Taylor polynomial, and then we're going to be centered at c equals 1, and we're going to go out to n equals 4. So the first thing we want to do is we want to find in derivatives. And the more derivatives we work with, the better our approximation. Like the further out we go, the better our approximation. So that is going to be our first step. So we're going to find in derivatives. So our function is the square root of x. And then we want to find the first derivative. So we'll just use power rule here. And then we're going to find our second derivative. And then our third derivative. And then finally our fourth derivative. Okay, so that is our first step. So we need to go out to the fourth derivative. And then our second step, we're going to evaluate each derivative at our center point, okay, so at C. So what we're finding right here, so just to make sure we understand that, is what we're looking for is like, what is f double prime of C? You know, what is f prime of C? What is f of C? And then we have to go all the way out to the fourth derivative. So that's what we're looking for right now, is we're trying to figure out what are these numerical values to help us find that coefficient. Okay, so that is what we're working on right now. So then I'm going to evaluate each of these functions at C equals 1, right? So at C equals 1. And so why did we choose 1? Well, you didn't, but why did I choose 1? Is because those are numbers that we can evaluate quite easily. 1 to a power is just going to be 1, right? So 1 to the half is just 1. And then now I'm going to evaluate my first derivative. So this will be 1/2 times 1 to the power of -1/2. Well, 1 to the -1/2 is just 1. So 1 times a half. And then same thing for the second derivative. So this would be -1/4 times 1, which is -1/4, right? See how lovely that is to evaluate, because we know 1 to a power will just be 1. And so that would be 3/8 times 1. And then finally for our fourth derivative, that would be -15/16 times 1. So now that we've evaluated each of those derivatives, we can go ahead and create our polynomial. Okay, so we're going to create the polynomial. In this case, it'll be a Taylor polynomial. So it would be Maclaurin, right, if our center was 0. And so again, what are we using? We're using that rule that we're going to take the nth derivative, evaluate it at C. We're going to multiply that by x minus c to the power of n. So the derivative we used has to match the power. And then we're going to divide by n factorial. So, right, so our derivative needs to match our power, which needs to match our polynomial, our factorial. Okay, so let's go ahead and find that polynomial. So there's two different, kind of standard forms for us to write out that polynomial. So if it's a Taylor polynomial, we could do p with a subscript of 4, meaning we approximate it out to the fourth derivative. But sometimes they will actually use t for Taylor. Okay, so either one is fine. So so our book uses p, so that's why I do, but I know that I'll sometimes go back into that t format. Okay, so here we go. So we're going to start with this first one right here. So we have no derivative, right? So we have 1, and then this would be x minus 1 to the power of 0, because I didn't use a derivative, right? And then divided by 0 factorial. And then now I'm going to go to my first derivative evaluation. So that would be plus 1/2, and then x minus 1, and it was my first derivative, so a power of 1 divided by 1 factorial. And then now I'm going to go to my second derivative, so that would be -1/4. And then I used my second derivative, so power of 2 divided by 2 factorial. Then I'm going to go to my third derivative, so that would be plus 3/8. And then I used my third derivative, so third power over 3 factorial. And then finally my last one here, -15/16, and then x minus 1, that was my fourth derivative, so fourth power over 4 factorial. And we cannot leave it like that. So we do need to work on our simplifying skills here. So simplify but not distribute. You're simplifying your coefficients, okay? So you're simplifying your coefficients, do not distribute this out. And then sometimes in the process of simplifying these, you see a pattern that you can kind of refer to or work with, but we're just going to go ahead and simplify this. So I have a 0 factorial, which is just equal to 1, to the 0 power is equal to 1. So that would just be 1. and then plus, and then I have 1/2 divided by 1 factorial, so that would be just 1/2, and then x minus 1 to the power of 1. And then I have 1/4 divided by 2 factorial, so 1/4 divided by 2, I would just have a product there, so that would be minus 1/8, and then x minus 1, and then squared. And then I have 3/8 divided by 3 factorial, which is 6. So that would be 3 over 8 times 6 is 48. So 3 over 48. So what is that? 16? Yes. Okay. And then that would be x minus 1 cubed. And then finally, okay, I'm going to have to do some scratch work here. So 15/16 times 1 over 4 times 3 times 2. So let me do some dividing. That goes 5. So 5 over 80 and 148. 80 and 48, 128. There we go. So I'm going to grab a calculator here in a moment. Okay, so that would be, okay, so what I'm saying now is this is my polynomial, Taylor polynomial. So that is the first thing that they asked us to find. And so done, right? So there is our nth Taylor polynomial. And then now we want to use that to approximate what is f of 1/2. So now we're going to use that to approximate f of 1/2, meaning the square root of 1/2. So the square root of 1/2 is about, and so now I'm going to replace all of my x's up here with 1/2. So I would have 1 plus 1/2, and then 1/2 minus 1 to the power of 1, and then minus 1/8. And then this will be 1/2 minus 1, which is negative 1/2. So I'm going to go ahead and do that arithmetic as I go. And then 1/16, and then negative 1/2 cubed. So again, I'm just doing 1/2 minus 1. And then minus 5 over, that's an 8. And then negative 1/2 to the power of 4. So as much as I don't want to do this by hand, it is something I absolutely could do, right? Because so this would be 1, and then this is negative 1/2 times 1/2, right? And then minus, and then this would be 1/8, and then negative 1/2 squared would be 1/4, plus 1/16, and then negative 1/2 cubed is negative 1/8, minus 5 over 128, and then negative 1/2 to the 4th would be 1/16. So, right, this is definitely in my wheelhouse, right? Like I may not know how to find the square root of 1/2 without the aid of a calculator, but this is definitely something I can do. Oh, brother. Okay, so I could do, so I could totally do 128 times 16 by hand if I wanted to, right? But I'm going to use my calculator though. So that would be 2048. So this is where I'm going to like bail on doing this by hand. Like I know that this is in my ability. Like this is something I could absolutely do by hand, right? And as well as you, but I'm not going to. So I'm going to use my calculator to add up these guys right here. Even though I know I could do it by hand, I'm going to be totally cheating here. Whipping out the calculator, adding these up. I also know that this is something I could do by hand as well, right? I can do long division by hand. So 2048 divides into 1451, right? So I am going to cheat. I could do this by hand, but I'm going to steal away and I'm going to use my calculator here. And wait, let me double check that. Make sure I did that right. Oops. And I have my decimal in the wrong spot. All of a sudden I was like, wait, that doesn't look right. Okay, so that's what I got when I did that by calculator, even though I know I can do that by hand. And then if I did the square root of 1/2, so if I did that, I get, so in a calculator, I'm getting that that's 0.707. So this is accurate to the nearest thousandth, or to the nearest hundredth, right, the 70. And then it's off by 1,000th. And I only went out to 4 terms, which like that was kind of tedious, but I only went to 4 terms. And so that's pretty amazing. And so that is that approximation. So I kind of want to show you this a little bit on Desmos as well, so you can see like where that's, kind of that anchor point, so I'm going to switch into Desmos here. And I have like the first So what I did was, so this is going to be my Taylor polynomial is what the red graph is, and then y equals the square root of x is the one I'm trying to approximate. So this is my P2, right? So this is my power of 1. So 1 plus 1/2 x minus 1. So like you can see that the red graph is a horrible approximation, right? Because it's not anywhere near that. So now I'm going to add in the next term. So the next term was 1/8. So I'm looking at the expansion that I got, and then x minus 1 squared. So then now if we look, I can see that, okay, in that particular section, like, hey, that's not a terrible approximation, right? Like it's like this blue graph, right? Like that's my quadratic. Excuse me, the blue graph is my square root graph, and the red graph is the quadratic. And so I'm anchored at 1 here, right? And so it bend pretty nicely around 1. And that's only to the power of 2. So let's go ahead and add that third power. So 1/16, and then it was x minus 1 cubed, right? I'm just copying down what I got in the notes there. And now look at how well the red and the blue graph are starting to match up, right? Like they're bending around each other nicely. Okay. And again, like that's only out to, oh, I did not just delete that. Okay. So, but you get the gist. And I didn't even write out my fourth one. And so that is what we're working on, right? Like that is cool, right? That is cool. So I'm creating a polynomial that wraps around that square root graph. And the more terms that I add, like the closer the functions become the same. Okay, so there is that piece. So let's take a look at the second thing that we have to take a look at. So the remainder of a Taylor polynomial. So this is, will remind you of kind of the alternating series approximation remainder, right? So it will kind of remind you of that a little bit. So this is the remainder of a Taylor polynomial. This is also known as the Lagrange form of the remainder, and I'll refer to it as that. Okay, so the Lagrange form of the remainder. All right, so this is what it says. So to measure the accuracy of whatever we're approximating, right? So how accurate are we on approximating that function value that we just did? You can use a concept of a remainder. And so your remainder is, like your polynomial approximation plus like how far you are off should equal your function. And we won't actually be able to find the remainder. Like we're not going to be like, oh, you're 2/10 off, right? Because we're using it to approximate irrational numbers. And so we're not going to be able to say we're 2/10 off. Okay, so we can't do that. So our remainder will be like, just like we have here. So whatever our error is, our remainder will be less than or equal to some number value that we'll create and find. Okay, so we won't know exactly what it is. We'll just be able to come up with some sort of upper bound for it. And the more accurate we are, for our remainder, the more we can say how accurate our actual function is. Okay. So if our function is differentiable through the order of n plus 1, right? So if we did a Taylor polynomial, so like on the last one we did P4, right? P4, we have to be able to get to that fifth derivative because we will be looking at the, first neglected term, okay? So we would be having to go out to the fifth derivative for that. That's what that's saying there. And then you're on some interval I containing C. So we have to kind of have an interval that we're looking at in which we are centered or anchored about. And then for each x on the interval, there exists some value of z that we will never, ever be able to find. So z will be outside of our ability to find, but that is okay, because that's why we're finding a range. Okay. So we're not looking for z, we're looking for, where does z land? Like, what could it be? Not what is it? So then our remainder, okay, so this is our Taylor polynomial right here, right? This is our Taylor polynomial. And then, so Tn, or Pn, whichever way. And then plus our remainder is going to equal exactly our function. And remember, we don't want to know that the remainder is 12. We want to know that it's less than or equal to 12. We don't want to know that it is 12. Like, we can't find that. So this is our rule for finding it, okay? So this is like how we find that remainder. And so this is that kind of reminiscent piece of the alternating series remainder in that you are at n plus 1, right? N plus 1, n plus 1. Okay. So again, z is not what we're looking for. Z is just, this is going to be like values that we're searching for. And so so the way we want to look at this, okay, is that, the f of n plus 1, that value here, we're really just looking for a maximum value, like an upper bound for what it could be. Okay, so we're looking for, it's like, what is the largest that the derivative could possibly be on the interval between x and c. Oops, that should say on the interval of x and c, okay, right? Because that's where this is coming from, on an interval between x and c. So we're just looking for, like, what is that maximum value? Like, what is the maximum y value on your function from x to x and c? So for example, like if we had, I don't know, so let's say that, f cubed of x was, I don't know, 3x to the negative 5 halves or something like that. And we are centered at 0 and we're approximating at 2. Then we would look at the third derivative, and I probably should have picked something I knew how to graph. That's some sort of radical. We would look somewhere between 0 and 2 of this graph right here and see, like, what is its maximum value. And we are looking at absolute value. So we would look at, the graph of this in an absolute value form, like what is its max between 0 and 2, okay? All right, so with that said, so let's go ahead and take a look at a problem. All right, so for this first one right here, that we're saying that we have a function that has derivatives of all orders on the interval from -1 to 1. And we're assuming that f of 0 is 6, f prime of 0 is 8, f double prime of 0 is 30, and the third derivative evaluated at 0 is 48. And then we know that the fourth derivative, right, has to be less than or equal to 75. So it's maximum value, so the fourth derivative cannot ever go above 75. And then this is true for all values of x on the interval from 0 to 1. So here they want us to find the third degree Taylor polynomial. So the third degree Taylor polynomial. So we're using the rule from the front side, right? So that would be f of n c times x minus c to the nth over n factorial. And then I am just giving you these numbers. That's what all of this stuff is here, right? Not making you find derivatives. I'm just giving you those numbers right off the bat. I am so kind. All right, so let's go ahead and do that. So this is the no derivative form, so that would be 6. And now catch this at about x equals 0, so that means c is equal to 0, right? So that would be 6, and then this would be x minus 0, right? To the 0 power, because it's no derivative, divided by 0 factorial. And then now let's go to the first derivative. So the first derivative is 8. So then that would be x minus 0. That was the first derivative, so power of 1 over 1 factorial. Now for the second derivative, so plus 30, and then x minus 0. That came from the second derivative, so power of 2 over 2 factorial. And then finally, third derivative, because we're looking for the third degree. So that would be plus 48, and then x minus 0. That came from the third derivative, so third power over 3 factorial. And then let's go ahead and simplify that a little bit. So this would be a Maclaurin, right? Because we're centered at 0. So 0 power, that's equal to 1. 0 factorial is equal to 1. So that would be 6, and then plus 8 divided by 1, which is just 8, and then x minus 0 is x. 30 divided by 2 is 15. And then x minus 0 squared, or x squared. And then 48 divided by 6, which would be 8, and then x cubed. So there would be my Maclaurin or Taylor polynomial, right? And then now use your answer from part A to estimate the value of 0.2. So f of 0.2 would be about equal to 6 plus 8 times 0.2 plus 15 times 0.2 squared, and then plus 8 times 0.2 cubed. And then just like a Riemann sum, like you would not want to actually multiply that out. You would leave it just like that. I mean, you obviously can multiply it out and add it out, but it is not something that you have to do. So find the maximum possible error in making this estimate. So this is asking for that Lagrange error. Okay, so that Lagrange error. So we would usually use E to represent, like, this is the error, and then we're going to say absolute value of it, right? So we're going to take that plus or minus version. So that error has to be less than or equal. Okay, so let's look at that rule, right? So the rule that we're looking at is this one right here. So the f of n plus 1, right? N plus 1. So our n was 3, right? Because we went out to the third derivative. So that would be f of 3 plus 1, so the fourth derivative. And then z, right? We don't know what that is. And then x minus c. So x is what we evaluated at, which was 0.2, minus my center, which was 0, to the n plus 1, so 3 plus 1, so power of 4, and then divided by 4 factorial, right? So 3 plus 1. So once we have that, now we have to figure out a numerical value for this piece right here. And we don't want to actually know what it is. We just want to know what is the maximum it can be on the interval from 0 to 0.2. Well, we were only given its max value between 0 and 1. So that's what we'll use. And we see that the fourth derivative cannot be above 75. And maybe there is a fine tune, like it could be fine tuned if we knew what the max was from 0 to 0.2, but we don't. So we take what was given, which is 75. And so then we're going to fill that in. So then our absolute value of our error is less than or equal to 75 over 4 factorial, and then 0.2 to the power of 4. And then if we needed to have a decimal value, we could do that. Otherwise, and when we do convert to decimal, make sure you go out to the 1,000. Okay. All right. So again, we are just using that formula. And then what we're making sure that we're paying attention to is, like, what are each of these values, right? So when we look at this formula here, x is what we evaluated at. So that would be the 0.2. C is what we were centered at, which was 0. And then n is what was the derivative we went out to in our approximation. And so that would have been 3. Okay? All right, let's take a look at one more example here. So we're going to use Taylor's theorem, so also known as the Lagrange error, right? To obtain an upper bound, right? Because we don't know its actual value for the error of the approximation for the function e to the x, and then we're centered at 0, okay? And then if we look here, the approximation, we went out to 5, so then we know n is equal to 5. We approximated at x equals 1. We were told that we were centered at 0, right? We were told that we were centered at 0. So our error is going to be less than or equal to f and then n plus 1, right? So n plus 1. So that would be 5 plus 1, or 6. And then times x minus c to the n plus 1, so 6, divided by 6 factorial. So what we were not given is we were not given this value or anything with that. So then that is left up to us, right? So that means we have to find f of, or to find the maximum value of this, right? To come up with a number value for this. Since it wasn't given to us, then we need to go out to the 6th derivative. And we have to find the maximum value of that on the interval of x and c. So on the interval from 0 to 1. So on the interval from 0 to 1, we have to find that value. Okay? So that means we have to go out to the 6th derivative. So that's what we're going to do over here. So I know f of x is equal to e to the x. So now that first derivative would be e to the x times the derivative of x, which is 1. The second derivative, e to the x times the derivative of x, which is 1. So do you see why I chose this one? Because, going out to the sixth derivative, easy peasy. So the sixth derivative would be e to the x. You're welcome. Okay, so now we have to find the maximum of that graph. So I'm going to graph e to the x, which looks something like that. And I'm looking on the interval from 0 to 1. So I'm looking between here and here, right? What is the maximum of that section? And that would be right here, which would be e to the x, or e. And so this is where there's a little bit of forgiveness here. So we could do a few things here. We can say that that error is less than or equal to e to the first, right? And then 1 to the sixth is 1 over 6 factorial. So there also is a component of, because e is rational, that it would not be wrong to say something along the lines of the error is going to be less than or equal to e is under 3, right, over 6 factorial. So this would be an accepted answer. So would this, right? Because you still have this upper bound. So there are components sometimes where instead of using that irrational number, we actually will just use, some sort of integer value that's close to it as well. Okay? All right. And that is the end.